Welcome back, everyone, to another deep dive into the OEIS. It's amazing to see so many number theory students tuning in each week. We must be doing something right.
I'm thrilled to be here. The OEIS is a treasure trove of fascinating sequences.
Right. Today we are going to look at one that seems simple at first, but believe me, it's going to get really interesting.
Oh, I believe it.
Okay, so today we're looking at A000165, which is the double factorial of even numbers.
Great choice.
So the formula is 2n equals 2 to the n times n factorial. What's actually happening here?
Well, let's start by making sure everyone understands what the double factorial means.
Yeah, the notation is a bit intimidating.
Right, because it uses those double exclamation points, but it doesn't mean we're doing the factorial twice. Like n would be a totally different beast, much, much larger.
Right.
The double factorial, it means we're multiplying all the positive integers up to a certain number, but only the ones that have the same parity. So either they're all even or all odd.
So today, since we're dealing with the double factorial of even numbers, we're multiplying all the even numbers up to 2n's.
Precisely.
Okay.
For example, let's take 6 double factorial. That would be 6 times 4 times 2, which gives us 48. So we're only using the even numbers in the calculation.
Got it. Now, I noticed in the OEIS entry that there's a connection to combinatorics here.
Yeah.
Specifically with the idea of pairing objects.
Yes. The double factorial of odd numbers, which is written 2n1, that counts the number of ways you can pair up 2n objects.
Okay, I think I need an example for this one. So imagine we've got 2n guests at a dinner party. How many different ways could we pair them up at the table?
That's a great way to think about it. Let's say you have 6 guests. The first guest has 5 choices for a partner. Once they've made their choice, the next guest has 3 choices.
Right.
And so on. So you get 5 times 3 times 1, which is 15, and that happens to be 5 double factorial.
Wow, so the number of pairings gets really big really fast as you add more guests. But how does this connect back to the double factorial of even numbers? Not the odd ones.
Well, the OEIS entry links 2n to something called the automorphism group of the graph of the n-dimensional hypercube.
Okay, hypercube and automorphism group. We might need to break those down a bit for our number theory students.
Sure. Imagine a square, which is a 2-dimensional object, right? Then we have a cube, which is like a 3-dimensional version of a square. A hypercube is like a cube, but extended to higher dimensions. It's hard to visualize, but the concept is similar. Now, the automorphism group of a shape basically describes all the ways you can transform that shape while keeping its fundamental structure the same.
So for a square, you could rotate it or flip it, and it would still be a square. Those would be part of its automorphism group.
Precisely. And for a hypercube, the automorphism group includes even more complex transformations in higher dimensions. The amazing thing is that the size of this automorphism group for an n-dimensional hypercube is given by the double factorial of 2n.
Wow, so we're saying that the same numbers used to count dinner party pairings also describe the symmetries of these mind-boggling hypercubes. That's incredible.
It is. It really highlights how seemingly simple mathematical concepts, like the double factorial, can have such unexpected connections to areas like geometry and group theory.
And this is just the beginning. There are even geometric interpretations involving volumes of higher dimensional spheres. But I think we're going to have to save that for part 2 of our deep dive, so stay tuned because it gets even more mind-blowing.
Welcome back. We were talking about higher dimensional spheres.
Yeah, I'm still kind of stuck on that. How can we even picture what a higher dimensional sphere would look like? It's pretty hard to wrap my head around.
It is a challenge to try to visualize anything beyond 3 dimensions, but we can think about it in terms of analogy. You know a circle, right?
Yeah.
A circle is a 2-dimensional sphere. And then a sphere like a ball, that's a 3-dimensional sphere. So a 4-dimensional sphere would be like the next step in that pattern. But it's embedded in 4-dimensional space.
Okay, so we're extending the idea of a sphere into dimensions we can't really see. How do double factorials fit into all of this? I'm not seeing the connection yet.
Well, double factorials appear in the formulas for the volumes of these higher dimensional spheres. It's a bit like how pi shows up in the formula for the area of a circle and the volume of a 3-dimensional sphere.
So they're capturing some fundamental property of these higher dimensional spaces, even though we can't picture them directly.
Exactly. And it shows how these numbers can be connected to concepts that are beyond our everyday experience.
Okay, let's move on. The OEIS entry for A000165 also mentions connections to some other sequences. One that caught my eye was the binomial mean transform of A000165. Can you explain what that is?
Yeah, the binomial mean transform is a way of creating a new sequence from an existing one. It uses binomial coefficients, which you might remember from Pascal's triangle.
Oh yeah, binomial coefficients. They tell you how many ways you can choose a certain number of objects from a set.
Right. So the binomial mean transform uses these coefficients to basically calculate the average values in the new sequence.
And the OEIS entry is saying that applying this transform to A001907 produces our double factorial sequence. It's amazing how all these different areas of math are connected.
It is. It really shows the elegance and interconnectedness of number theory. Things that might seem like separate areas of study often turn out to be closely related.
You mentioned earlier that double factorials also come up in fields outside of pure math, like statistics and physics. Can you give us some examples?
Sure. In statistics, they appear in the formulas for the moments of the normal distribution. The moments describe the shape of the distribution, and for the standard normal distribution, the even moments are given by double factorials.
So even when you're analyzing data, these double factorials are there. What about in physics?
Well, in quantum mechanics, if you study the quantum harmonic oscillator, you'll come across solutions that involve double factorials. They also show up in statistical mechanics and even in quantum field theory.
It's amazing to think that these numbers can have such profound applications in understanding the physical world.
It just goes to show that math is not just an abstract game. It's a powerful tool for understanding reality.
Let's recap for our listeners. We started with the double factorial of even numbers, which seemed pretty simple, but then we saw how it ties into combinatorics, higher dimensional geometry, statistics, and even quantum mechanics.
It's a great example of how a seemingly simple mathematical concept can have far-reaching implications. And there's still so much more to explore.
Can't wait for part 3. Welcome back. It's amazing to think about all these connections we've found between double factorials and so many different areas of math and physics.
It really makes you wonder if there's something deeper going on, like some underlying reason why this one sequence keeps showing up in such diverse areas.
Yeah, I'm starting to think that too. We started with just the numbers, but now we've seen how double factorials relate to pairings, symmetries, volumes, even probability and quantum mechanics. Maybe these numbers are pointing to some kind of hidden structure in the universe.
It's a fascinating idea. Sometimes the connections in math are right there on the surface, like how the formula for double factorials directly relates to counting pairings.
Right.
But then in other cases, the links are more subtle. Why should these numbers appear in quantum mechanics and in the formulas for the shapes of higher dimensional objects? Is it just a coincidence, or is there a deeper reason?
It almost makes you want to believe in mathematical magic, like there's a hidden code that explains everything.
Maybe not magic, but I understand the sentiment. Mathematicians are always searching for those deeper connections, for unifying principles that explain why math works the way it does. It's possible that there's a whole framework we haven't discovered yet, a new kind of math that will explain why double factorials and other simple concepts have such a huge impact on our understanding of the world.
It's pretty mind-blowing to think about. It's like we're exploring this uncharted mathematical landscape.
Exactly. And the OEIS is an amazing tool for anyone who wants to do that. Every entry is a starting point for discovering patterns and connections and mysteries.
So if our listeners want to learn more about A000165, the OEIS entry is the perfect place to begin.
And as you explore, don't forget to ask questions. What patterns are there? What connections can you find? What mysteries haven't been solved yet?
It's what makes number theory so exciting.
Absolutely.
Well, it's been an incredible journey exploring the world of double factorials, from dinner parties to higher dimensions and quantum mechanics. This one sequence has led us to some of the most amazing ideas in math.
It shows you the power of mathematical thinking.
I want to thank you for being with us on this deep dive. I know I learned a lot, and I hope our listeners did too. And to everyone out there, keep exploring, keep asking questions, and stay curious. We'll be back soon with another deep dive into the OEIS, but until then, happy exploring.